So thank you very much for that intimate introduction. Thank you, thank you. So it's really a great pleasure to be here to give this lecture. So I thought I'll start by thanking the people who made it all possible for me to be here at all. So first are my two advisors, Bob Gallagher and John Cisiklis. They really started me on the right path. Without them, I would definitely not be here. And Bob Gallagher, he was my advisor, and is still my advisor. In fact, this talk, I went through 3 or 4 rounds of dry run with him. So of course, I am the ultimate responsible for the talk, not him, but always an advisor. So I would also like to thank my students and my postdocs. Without them, there will be no reason for me to be here. At the end of the day, the most important output is not papers, it's not awards, but are people. And these people are the ones who made it all worthwhile. I would like to thank in particular Sohei and Fazan and Sriram and Pramod and Ilan for helping me with this talk. They gave me a lot of very valuable feedback. Finally, my family. Without them, I'd definitely not be here, that's for sure. My parents, JT and Evelyn, my wife, Leah, my daughter, Ching Ching, my sister, Nadia, Uncle John, and Man, they're mostly all here. Yeah, they're definitely here. They're definitely here. So thank you very much. All right. Okay. So let me say a few words about what I actually want to do today. So all the talks I've given are very technical talks on very specific topics using tools from the field. I want to do something different today. I want to give a talk about the field itself. I want a deeper understanding of the field, the spirit, the energy of the field that keeps it kicking and alive after so many years. I think our field is at a crossroad, and I'm hoping my talk will contribute towards a deeper understanding of ourselves and help us chart the path forward. So, what is the essence of the spirit? I would like to summarize it in this picture. So the 2 facets of information theory, beauty and utility, not in isolation, but in a full cycle, interacting with each other, providing energy to each other. This is the picture I want to elaborate on using stories from my own research. So this is a very personal view. And I would like to also take this opportunity to highlight people who helped me understand this picture over the years. So my story started at MIT, Laboratory for Information and Decision System, where I did my graduate work. I arrived at MIT. I wanted to study machine learning. Yes, believe it or not, machine learning. But then I took a course from Bob Gallagher in information theory. And I got hooked onto it ever since. So I still remember that very first lecture in information theory. Bob said the following: good theory should prune rather than grow the knowledge tree. I have no idea what he was talking about. I thought as a graduate student, my job is to add a leaf or a twig to that tree to make it bigger. What is this guy talking about? Nevertheless, it sounds wise. So I thought I want to be his student and I want to study information theory. He gave me 2 very good bits of advice. The first thing he told me was, don't work in information theory. Yes, it's true. The second thing he told me about was near the end of my graduate school. He told me that, hey, you didn't work on information theory, but keep an eye on wireless. So to see how wise this guy was, let me plot something. So this is a plot of the citations to Shannon's total collection of papers over the years. starting from 1978 when I have the data. So this is, to me, a very rough proxy for the influence and the visibility of the field. So here we have the number of papers from 1978 to my graduate school days in the order of a few hundred. Not very visible. So I was really lucky that I did a thesis on something else, networking. And that's how I got a job at Berkeley. Thank you, Bob. But after I graduated, the field exploded. And I was lucky enough to follow Bob's advice again to move into wireless. And I was able to catch this wave. So, as Rudiger already mentioned, my first job was at Bell Labs. That's actually where I met Rudiger. I also met Stephen Henley, which was really important for me. He was already working in wireless, and he was trying to persuade me to work into wireless as well. Now, we were apartment mates. And look at this place. There's nothing happening around there. So every night, what do? Nothing to do. We just talk about research. That's how I got into wireless. The problem we were talking about was opportunistic communication. So this is the wireless channel. At that time, there was a very important result by Andrea and Pruning on analyzing the capacity of this channel under perfect channel state feedback. And what they showed was that to communicate optimally, one has to communicate opportunistically at the peaks of the channel. Several people, instead of in contrast to the deep phase where other people worry about. So many groups are trying to generalize the result to multiple users. The first result was obtained by Knob and Blay, where they analyzed some capacity and where they show a phenomenon called multi-user diversity, where if you have more users, basically what they observe is there are more peaks to exploit and therefore more gain. We follow up with analysis of the entire capacity region as well as the delay limited capacity. So let me show you that result that we got. So this problem was an information theory problem, analyzing the capacity region. But turned out, at the heart of it, Rudiger already alluded to, is a resource allocation problem, optimal resource allocation problem, how to allocate power across users at every fading state. Now, the problem seems rather complicated because, as we all know, there are exponential number of rate constraints as a function of number of users. So it's a very complicated problem, seemingly. But we identify a very simple structure called polymetroid, which leads to a very simple solution. The solution was obtained by defining a marginal utility function for each user separately. And then you allocate power by just following the user, which gives you the largest marginal utility. So here, red, followed by blue. And this will give you the power allocation at this fading state. So you decode blue user first and then red user. And that's it. Very simple solution. Now, we did a lot of theory for a few years. And then I thought, wait a minute, I'm going to get out of touch. Let's see what the real world is like. So I went to the real world. The real world is equal to Qualcomm. So I was really fortunate to meet two people there, Andy Verterby, who hired me. I find myself really fortunate to be hired by him because at that time, at Qualcomm, there was a very healthy skepticism of academics. But nevertheless, he hired me. And then I met Roberto. Roberto was heading the group at that time designing the new generation of air interface for Qualcomm. In contrast to the existing interface, where Qualcomm was famous for CDMA, the downlink of this new interface was actually TDMA. And TDMA, the key problem, is the resource allocation problem across the users. Now, at that time, they already have a scheduler, so that was not the project they assigned to me. But the scheduler, I noticed, was completely ported over from the wireline world, unchanged. But knowing what I knew from information theory, I knew we could do better. So 6 months gone by. My only output in the 6 months is 3 lines of MATLAB code. This is the proportional fair scheduler. I kid you not, it's 3 lines. Now, although it's only 3 lines, it captures all the essence of what we learn in information theory. So proportional fair scheduler is equal to multi-user diversity, where we learn from Knob and Blay, plus fairness across users, which we control using utility function like we did in the information theoretic analysis, plus delay control, which we learned from our delay limited analysis. So 18 years have gone by. Unbelievable. I talked to my Qualcomm colleagues again 2 months ago, asking them, so what happened to those 3 lines of MATLAB code? So they were very kind, they helped me to survey all the infrastructure companies around the world. And it turned out that this scheduler is the default scheduler for all 3rd generation and 4th generation best effort data. So green area is 3G and 4G deployment. What does that mean? 10 million base stations running this scheduler, serving 2.7 billion subscribers. So I designed the algorithm, but it was based on a whole body of work done by the entire community. So I view this algorithm as our community's algorithm. And we were able to maximize the impact by riding on the wireless technology wave. So we have come a full circle. We started with a messy problem in the real world problem. We abstract a mathematical structure, polymetroidal structure. And then we give back to utility, to the real world, by giving this algorithm. So I think this work was really perfect timing. It was exactly the right time. And I was lucky because I was at the right time at the right place. However, the more important thing to observe is that we're not only lucky. It's because the theory prepared us for this. And when the opportunity came, we strike. So the second story I want to tell is the MIMO story. So multiple transmit, multiple receive antenna was a very exciting research direction in the late 1990s and early 2000s. There were 2 views. The diversity view, using antennas to reduce the deep fades. And in the modern view, the multiplexing view of sending parallel stream of traffic. So at that time, these 2 views represent, in some sense, 2 groups of people in the community. Diversity was mainly focused on by coding people. You want to maximize diversity, you want to maximize coding gain. Multiplexing was focused more on the capacity people, analyzing the capacity of various configurations. With Lijong Zhang, my student at that time, we were really puzzled. How can the same channel have 2 such different views designed by 2 bodies of people? We're really puzzled, and what we learned was puzzles represent opportunities for research. And we seized that opportunity, and we came up with the diversity multiplexing trade-off. So one picture unifies diversity and multiplexing, no longer in isolation, no longer separate, but together in one picture. When this picture emerged, I finally understood what Bob Gallagher told me in that very first lecture, what pruning the knowledge tree means. Here we have diversity, multiplexing, 2 branches of a tree. We unified it into one. So Pramod and I were talking about writing a wireless book at around that time, for a few years actually. When we got the diversity multiplexing trade-off result together with the opportunistic communication results, we felt we were ready. After working 2 hard years, we came up with this book, Fundamentals of Wireless Communication. This book is equal to information theory, which provides the underlying theoretical structure of the book, but plus something else, which we call system view. And the system view is a view that when you design a wireless system, the performance of the wireless system is not only dependent on the performance of the individual components, but how they interact with each other. And the system view provides the broad engineering structure for this book. And the system view, we learn a lot from Rajiv Loraya, one of the best engineers I've ever met in my life. He was starting Flareon at that time. We were interacting with him very closely. And he was designing an entire wireless system from scratch. And therefore, the system view was central to his success. And we learned from him, and it turned out the system view was also central to our success. So 12 years have gone by. Our book has achieved a very broad impact, much more than we would expect when we worked on it. So I look back, I said, why? How could our book provide this impact? That helps me understand one thing about information theory, which is very odd, is that we know information theory is beautiful because individual results are beautiful. But this book tells us a bit more. It tells us that information theory is beautiful also because it is coherent. It brings structure to a whole field, wireless communication. And that structure enables our book to be understandable as not a collection of results, but a whole picture. So after finishing this book, I got really burned out about wireless. After working on this 2 years, day in and day out, I was really burned out. But then there was one nagging problem I really want to solve for many years I have not been able to solve, the interference channel. So at that point, I felt that I have a pretty good understanding of the high SNR behavior of wireless channels. And so I thought maybe we can give it one last crack. And with Raul, my student, and Hua, promote student, who was visiting us at that time, we finally kicked the door open. The result was the analysis of the capacity of that channel, characterization to within 1 bit per second per hertz. Now, using this result, we can come up with a simple picture. How does the interference limited capacity, that's the high SNR capacity, as a function of the strength of the crosstalk, the interference strength? And this is the result. So as you can see, to us, it was a surprising result because it's not only not monotonic, it goes up and down several times, twist and turn. So Tom Cover said in his Shannon lecture that good theorems are like good jokes because they're surprising. And I hope he would consider this a good joke. So it turns out it's not only a result by itself, but it hints to something much broader. So in proving the converse of our result, we borrowed a very key idea from Al-Gamal and Costa on the analysis of the deterministic interference channel, a deterministic interference channel. So the connection was inspirational, very important, inspirational. But with Salman and Suhas, we decided that maybe there's a way to make that not inspirational, but concrete, by actually come up with a concrete deterministic channel to approximate the Gaussian channel, to simplify the matter. And we were able to succeed, not only for the interference channel, but for entire wireless networks. But applying to interference channel, you get this specific interference channel, deterministic interference channel, and the capacity of this is exactly that curve I plot in the last figure. So here we are, pruning the tree again. On the left, we have our Gaussian networks, complicated superposition of signals, broadcast of signals, Gaussian noise. On the right-hand side, we have a simpler network, wide-line network, much well understood. For example, we have the max flow min-cut Ford Fulkerson theorem. Our deterministic model enables us to connect these two worlds, to prune these two branches into one. And more importantly, we were able to exploit exciting results that were developing at that time on wide-line network in network coding and port it over, to some extent, to Gaussian networks. So this problem, this story, emphasized the importance of the use of simple models. Simple models have been with us since Shannon. What we showed here is that models that are simple can be simplified even further. So now here we are, after wireless. I've been thinking about in the past few years, how should we think about broadening information theory, broadening information theory. So why am I thinking about that? In part, it's because of intellectual restlessness. So I guess really good I can go to sleep in 1 second. But perhaps that's because I'm restless all the time. But another reason is because of this curve that I showed earlier. So this is a reminder, a plot of the citations to Shannon's collection of papers over the years, a rough measure of the influence of our field. Let us extrapolate this plot. It seems that this explosion will continue. But if you look carefully, this plot is only up to 2013. Something happened afterwards. So this is up to now. So it seems that we do need to broaden our field, not only for intellectual restlessness reasons, but for pragmatic reasons. We want to keep it going on this curve and not on this curve. So how do we broaden information theory? That's the question. That's the million-dollar question. Whenever you have a question, what do? Well, we add to one of these citations. We refer to Shannon. So Shannon, in his first paper on the topic, said the following. The fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected at another point. Frequently, messages have meaning. These semantics aspects are irrelevant to the engineering problem. So in two beautiful sentences, Shannon defined what his theory is and what his theory isn't. In thinking about how to broaden information theory, one can think about two different directions. First, one can think about perhaps we can find some other types of messages, not communication messages, but some other types of messages to reproduce. That's one direction. Another direction is we can try to tackle the question of meaning. Can we do something to extract meaning from messages? So I'll give one story in each direction. I think these two directions are different in flavor, and I hope to give some sense of what they are. So two stories. So the first story started at the Newton Institute in Cambridge in 2010. So I was attending a workshop, a program, actually a multiple months program in communications. For a random reason, I had to stay afterwards in Cambridge for a few extra months. So I said, okay, what's the next program? Statistical challenges arising from genome resequencing. No idea what that is. Nevertheless, I have time on my hands, so I went to a few talks. And what I heard there was mind-blowing. Because what I heard there was in parallel to the wireless universe, the wireless revolution. There's another revolution going on. It's the sequencing revolution, the revolution of sequencing genome, starting with sequencing the human genome in 2001. The cost, just like wireless, is powered by technological revolution. And the technology here is the sequencing technology. And the cost went down 5 orders of magnitude for the past 15 years. So from my experience in wireless, we know that if we could catch a technological wave, then there are interesting research to be done. Moreover, the key equation in sequencing is actually this. Sequencing equals biochemistry plus computation. And so I felt that I could potentially contribute. So let me focus on the basic problem in sequencing, the computation problem. There are many problems, but this is the basic one, the assembly problem. So we have a genome here. It's a string of about 3 billion long of symbols, A, G, C, T. The biochemistry is represented here by the sequencer, so-called shotgun sequencer. Because of imperfection of the biochemistry, we cannot read the sequence from beginning to end. So what we had is many randomly sampled reads, very short sample reads, substring, and we don't know where they are. We don't know where they are on the genome. Okay? So the question is, the assembler is to computationally try to put them back together, to align them to a sequence as hat. And that's the output. So this is not a communication problem, but S hat is a reproduction at one point of a message at another point. So this is another example. This is an example of a reproduction problem. So how do we solve this problem? One thing to observe is that this problem is actually pretty large scale. The message length, actually the length of genome, is 3 billion. And the received data, the total amount of reads, is roughly 10 to the 11 symbols. So from the get-go, this problem, you can see, is a very large-scale computational problem. So my experience in this problem can be summarized by this picture. Information meets computation. Shannon meets Turing. So this problem actually has been working on for about 2 decades by the computer scientists. And their basic result is that genome assembly is NP-hard. So I took a different point of view, being an information theorist. I first asked, let's find the information limit first. In other words, how much data do you need to actually reconstruct uniquely the genome with high probability? Now, this seems to be a very odd approach, especially for people outside information theory, because computation is the biggest elephant in the room, and we're avoiding that by asking a different question. What's going on? But we know from our experience in channel coding and decoding that although the problem is NP-hard in general, but achieving capacity because of the structure enables us to do it efficiently. And that was a very important experience I learned from information theory. So a natural question is, can we try to avoid NP-hardness problem by focusing on the information limit, by achieving the information limit? To do that, we need to first characterize the information limit. So that was the approach. So that was the approach, but the way to get there was very windy. We first start with a paper with Abolfazl Montahari and Guy Bressler, where we analyze this problem using a very classical information theory approach. What's a classical information theory approach to this problem? Is to give a very simple model for the genome. And a very simple model was the simplest model, IID genome, AGCT or IID. And we solved that problem beautifully. And as well as getting an efficient algorithm to get to the information limit. However, we're also pretty good engineers. And we have to be honest. So to be honest, what we do is we look deeper into our result and figure out, so what aspect of the genome is actually important for our result to hold? And it turns out that aspect is the repeat length statistics. That is, how many repeats of each length are there on the genome? And so we actually go and measure, because we already have genome sequenced by other people, what's the repeat length statistics like in the real genome? So this is chromosome 19 in the human. And this is the distribution. This tells me how many genomes are there at different lengths. And we fit an ID model on that, and we get this. So obviously, IID is not a good fit. There's a much more longer repeats. And so we knew that our ID model would not shed some light to the real problem. And in fact, we could not find out any good statistical model to describe this. So we changed approach. We're flexible. We changed approach, and we were able to find an approach where we could characterize the information limit directly in terms of the repeat statistics. So in other words, we bypass the model altogether. And here we describe the information in feasible instances. In terms of the number of reads and read lengths, this tells me that if the number of reads and read lengths is shorter than a certain amount, then we cannot reconstruct, no hope, not enough information. Now, once the information theorist sees a lower bound, then the question is, can we design an efficient algorithm to get there? A very, very concrete goal. And that's what we did. We find an algorithm whereby we can get close to the lower bound, and thereby characterizing the computational feasible instances. So the funny thing about this is, you remember I told you that computer scientist was telling us that the problem is NP-hard. So what happened? How did we overcome the problem? Well, one explanation is that the NP-hard instances are all hidden here in the information in feasible instances. And we don't care about them, since we're only focusing on the information achievable ones. And we show that they're computationally feasible. However, this is not quite the answer. We thought it was, but it was not quite an answer. Only recently, we figured out that actually there is a small gap between these two curves. And over the years, we've been thinking that it's just a nuisance. We need to remove it, but somehow we're just not smart enough to remove it. But turn out that this small gap cannot be removed. In other words, we cannot have all the instances which are information feasible also computational feasible. There must be NP-hard instances there. And this is a consequence of a very deep result in CS theory, connecting information and computation, which we're still exploring at this point. So you can see that with a new model, new approach, there's new problems to be understood. So the theory we've been doing for the past few years, one thing we noticed that we didn't get much attention from the assembly people, the people actually building the assemblers. Nobody's listening to us. Nobody's implementing our theory. What's going on? Where's Qualcomm? So I said, OK, there's no Qualcomm. So what do? We have to be Qualcomm ourselves. So we did. We have a courageous team of students and postdocs, a collaboration with Tom Cortate at Berkeley. This team is quite amazing, I must say. They actually work hard for a year to design a real assembler. And we got it published in the Genome Research. And we're pretty proud of that because this issue is a special issue on assembly, and it features almost all the leading assembly teams in the world. And a lot of these teams have decades of experience building assemblers, starting from the human genome days. And we are very proud that we could get a seat on the table. So how many lines of code? 30,000 lines of code. No longer 3 lines of code. No longer 3 lines of code. The software is really complex, but the output is beautiful. So this is one example of the output of this software, an assembly graph. Our output is actually more general than a reconstruction. When there is enough information to reconstruct, this graph will become a linear sequence, one line. The graph structure tells you not only repeats that you can resolve using information, but also the repeats that you cannot resolve, and it keeps that information in this graph. So we were able to assemble real genomes now. Real software, real genomes. We have looked at the data set, NCTC 3000 by the Pacific Health England, 667 bacteria genomes. The existing pipeline that we're comparing ourselves to could assemble 509 of them. 178 of them is unfinished, unassembled, fragmented assembly. And our software could assemble 148 more, leaving only 30 on the table. So, for example, E. coli here, unassembled by the existing pipeline, assembled together by HINGE, our software. Pneumonia, similar situation, 148 of these examples. So what did we learn about this picture during this project? A lot. For me, a lot. First, it introduces this idea of we don't have to use these simple statistical models. There are other ways of modeling reality that is more closely tied to data. So in communication, we have this separation. We usually have a simple model which separates the mess so that we can do theory. Here, we're breaking that barrier by using a directly data-driven model. But still, the theory is pretty beautiful. But more importantly, equally importantly, is the role of information and computation working together to solve this problem. Now, this is also a long-standing information theory tradition. Information on the one hand, the capacity. Computation on the other hand, how to get to capacity. We are, in some sense, borrowing on that tradition, pushing further into this area, where computation plays a very, very central role. So we have already told you 3 pictures from wireless days. Each story summarized by 1 picture. That is what I mean by beauty. 1 picture captures the whole story. Here we are in a completely different application domain, but yet still summarized by a picture. So the beauty of information theory knows no boundary. So let us move on to a second direction that I mentioned. Reproduction was the first direction. Meaning was the second direction. So let's go back to a concrete example, the sequence example again, and look at it from a broader point of view. So I have biological sample coming in. Sequencing generates reads. Assembly gives me a genome. One can think of this whole structure as the plumbing. It is the infrastructure of genomics. It's very important. It's the infrastructure. Everything is built on that. It is a combination of biochemistry and computation. Together, they must work together. And the goal is to come up with a very good reproduction of the genome. This is the infrastructure. But genome is not the goal. The sequence by itself has no meaning, no use, no purpose. To make use of it, we must add extra pipelines, additional pipelines, to extract meaning. Otherwise, we are not serving a real human need. One example of a pipeline, just to be concrete, is the prediction problem. I have my genome. I want to predict, will I get type 2 diabetes or not? What's the likelihood? This is a prediction problem. One example problem, many other pipelines. Extracting meaning. So if you think about the plumbing, the infrastructure, this problem is rather similar to communication, which is also an infrastructure problem. So in some sense, the assembly problem was a natural problem for me to work on, although it was in a different application domain. But philosophically, somewhat similar. However, when we talk about prediction, now we're moving into the domain of statistics and machine learning. The question is, will we information theorists have anything to contribute here? Let's see. So I'll focus on a very concrete problem. Prediction is a very broad problem, but the concrete problem is linear classification. So here I am in feature space, red and blue points. Each point, for example, may represent a genome of a patient. The blue and the red is labeling whether that patient has type 2 diabetes or not. And now using these training samples, I want to learn a classifier for a new sample, a new patient. The simplest classifier is a line. You partition a line, and on top of it, you say blue, and below you say red. Okay? Now, this is one of the earliest problems in pattern recognition and AI, the perceptron problem. The perceptron is an algorithm which computes this plane, this hyperplane, given the training samples. Now, this problem, perceptron solved, is in the case when these points are linear separable. The more general and more interesting case is when the points are not linear separable. Then what do? Well, a natural thing to do is to find a hyperplane that minimizes the number of misclassification, because that's your goal. So that's a natural metric to use. Unfortunately, this problem is NP hard. So again, we're hitting a computational limit here, NP hard. So a struggle of this field, pattern recognition field, is to come up with a solution which overcomes this NP hardness. And this line of work culminated in a very important piece of work in machine learning, the support vector machine by Cortez and Vebnik. We showed that this part is hard. So what they did was they cheated. They changed the metric to some other metric, roughly as a function of the distances of these points from the hyperplane. And with this new metric, they could solve this problem, and that predictor, that classifier, turns out to be very important, very useful. And it is one of the biggest results in machine learning in the past 2 decades. Now, it is very useful, but we're after beauty. Is it very beautiful? I would say not, because they did a heuristic change to the natural metric. So it's not theoretically consistent. Is there a different approach? So I claim that there is a different approach, and the different approach is based on an object that we are very dear to, entropy. So the whole story started with James in 1957, where he gave a principle for finding a distribution to model a random variable from data. And he proposed the following. First, you measure some statistics of interest from the data. You use that to describe the set gamma. And now you find a distribution P in gamma that is consistent with those statistics. which maximizes the entropy. In other words, you want to find the distribution which is least committal. Now, this sounds like a Bible from James or something, because it doesn't have any basis. It's just a statement that he made. And so people were skeptical in the beginning, rightfully. But 20 years later, a result by Topsol says that actually you can give a min-max interpretation to this. You can view this as choosing a distribution to minimize the worst case loss, where the loss is measured by log loss. And what Grunwald and David showed a few years later, actually 20 years later, 15 years later, was that, 25 years later, was that you can generalize this to general loss as well, and they defined a notion of generalized entropy, loss-dependent entropy, and you want to maximize that. On the other direction, James' result was also generalized to the prediction context. Now you want to find a distribution to help you to predict y, the label, whether I have diabetes or not, from the feature vector x. A result, very important result in NLP by Berger, showed that a very natural principle following this line of work is to maximize the conditional entropy of y given x. That is, you want to find a model which is not least committal about the effect of x on y. Now, we came on the scene last year, and what we saw was two branches. Hey, what do we do when we have multiple branches? By now you get the drift. We unify them. And we came up with a generalized principle for prediction, maximizing the conditional entropy of y given x, generalized to arbitrary loss function. And we applied this principle to many, many different loss functions, and we got very nice results. And a lot of them are models that people already know, so we were able to unify them into one thing. However, the more important thing is that when we apply L back to the classification problem, that is, L is the 0-1 loss, then we get something nice. And this is the maximum entry machine. So the support vector machine, a quick recap, is to find the hyperplane using the coefficients beta of minimizing the sum of the losses over the samples, where the loss is described by 0-1 loss. That is, if you classify it right, then you get 0 points. If you classify it wrong, you get -1 point. Okay? The problem is that this is NP hard, so what they did was they changed this loss to some other metric. Okay? So I would say useful, but not beautiful. In the maximum entry machine, you have exactly the same problem, change data. But now, instead of maximizing over the classifier, we maximize over the distribution, P, maximizing the conditional entropy of y given x under the 0-1 loss entropy. Now, like the Shannon entropy, this 0-1 loss entropy, and in fact any loss entropy, shares the same property. That is, it's concave. So this problem is actually always efficiently solvable because it's a convex optimization problem. We don't have to change the 0-1 loss to any other loss. And then once we have this P star, we simply just use the base classifier under P star. And the result is not one hyperplane, it turns out, it's two hyperplanes. Here we design blue and red, but in between, we randomize. So it turns out that unbeknownst to this whole community of people, that actually the right thing to do, I believe, is to do randomization in the middle. And that emerges from solving this maximum entry problem. And the randomization is, the bias is a function of how close you are to the hyperplane, not the same single bias. All right. And this structure only emerges after solving this problem. So it's not predefined by me, like in this case, and therefore lead to a bad problem. OK. So this is good. Now, it's beautiful, I think. But is it useful? So we evaluate on data sets. It works equally well, or even better than SVM. So we're quite happy with that. But usefulness is not just evaluation data set. Usefulness is also about impact. The question is, are we going to make a big impact? So to explore that question, let's look at our development of this theory, of two branches. We're going to collapse the tree into a timeline. So here we are, 1957, James, the beginning of the story, to our paper with my student Fazan in 2016, almost 60 years. This is our timeline. Let's look at the support vector machine timeline of competitor. It starts with Rosenblock with the perceptron, same year as James, 1957. Many things are happening that year. 1995, Vapnik and Cortez came out with the support vector machine. So they beat us by 20 years. So what does 20 years mean? 20 years means this. 20 years means 26,000 citations. So what happened was, not only the result was good empirically, but the result was a perfect timing. It was exactly the beginning of the wave of machine learning, and they caught that wave. Our result is beautiful, but it came 20 years later. So we're not going to get any of those 26,000 citations. Sorry to say. So you may say, it's bad timing. Timing is luck. We have bad luck. Shut up. But there's a bit more to the story than just luck. There's more to the story than luck. Let's first look at which journals published these 5 papers that led to our work. Physical Review, Computational Linguistics, Statistics, and NIPS. None of these journals are transactions. None of these papers are published in transactions. So I said, what's going on? Our field seems to have outsourced this problem to others. What is going on? Our field is about entropy. Why is our field not working on this problem? Why are we outsourcing to other people? So if I contrast this story to the wireless story, I would say the following. In wireless, we were prepared. We have done theory in communication for decades, before the wireless revolution came. So when the wireless revolution came, we were ready. We can contribute, and we made a big impact. This is not the case here. We were not prepared. When the machine learning revolution came, we were not prepared. We could not make the contribution that Cortez and Vapnik could. I believe if our field has put in more energy in this direction of work, we could have possibly, not for sure, possibly made this contribution and obtained these 26,000 citations. So who owns data science? 3 years ago, Bin Yu gave a nice presidential address. Said, let us own data science. Who are us? Us refers to statisticians. She wants to say that we need to compete with computer scientists. We need to co-own data science. This is her call to arms of statisticians. She came to give a similar talk at ISIT, if you remember, 2 years ago. If you also remember, at the end of the talk, I actually asked her this question. What about us, information theorists? You can check out her answer on the video. I will not tell you now. But more importantly, we should ask ourselves, are we ready to commit to have a place on the table in data science? Okay, so that's my question for the community. And my answer is clear. My answer is yes. We have the tools. We have the spirit. We can do it. Why? Because data science is about extracting information from data using computation. I hope my examples have shown you. We know better than anyone about information. We have worked decades on computation to extract information. If we take a holistic view together with data, we can contribute. So let me end the talk. I would like to take the spirit forward. We owned communication for 70 years. We have worked hard on it, blood and sweat. We developed a spirit of beauty and utility at the same time working together. Now I believe it's our time to broaden our field, to use this beauty and spirit and utility to conquer other worlds. Thank you.
Thank you very much, David, for this talk of big beauty and high utility. I guess you could see from the applause there was highly appreciated. I would like to open the floor for questions.
There's a question there.
So, a lot of this stuff is based on shotgun, basically breaking a mirror and putting it back together. So that's part of the plumbing. There's nanopore sequencing coming along. Does that change the picture, especially since it can detect methylation?
So nanopore, the question is, what happens if we change the technology? Nanopore sequencing was another one. In fact, our same assembler works on nanopore as well as other technologies. So I think our approach of the problem is that we try to be a little bit technology agnostic. So yes, we can apply on nanopore sequencing as well.
But you can do methylation with the other techniques?
I'm only focusing on the assembly problem here.
Lalita.
So Craig Venter made his name with this whole shotgun sequencing, right?
Gene Myers, you said? Sorry, what did you say?
Craig Venter.
Craig Venter, yes.
So he was the one who said, I'm just going to go randomly pick parts of the genome, sequence it, put it together. So how do they publish the genome if you still think it's an incomplete problem?
The genome, the assembly right now is fragmented. No, there's no single assembly. It's many, many parts.
Any more questions? Marco.
Yes, Salman. Sorry, I didn't quite understand I understand, so you were saying, let me repeat what you said. You were saying a lot of trends in data science is that when you get something hard like deep learning, everybody jumps on to the bandwagon, and then they move on to another type of deep learning architecture, perhaps. Is that what you're saying? And okay, and after that?
Getting the beauty, you have to do a lot of work to get the beautiful part. So by the time the trend is, so the patients get the beauty, may not pay.
Yeah, so that's a good question. We just have to have faith that it will pay off.
Marco?
Yes.
Can you say a word about where to place security crypto in this picture and the contribution to information theory?
Oh, this is very dangerous. You're trying to get me in trouble. If you remember, a few years ago, I asked a question after Prakash talk, and that got me into trouble already.
Marco?
So I won't go there.
You had the next question, Marco.
Yes. Yes.
What do you think the plan is about pruning community?
Yeah, so in some sense, if you think about a maximum entry result, it is to some extent pruning communities. Because if you think about the basic problem of prediction, one can think of work from statistics. For example, Fisher work on maximum likelihood. You can think of work from Vapnik, empirical risk minimization, which is the basis of deep learning, for example. And here we are, a third approach, maximum entropy. So we have different views of the same problem from different communities. So in some sense, it's pruning the community to some extent. So the point is that as we move away from communication We have to interact with other communities. And I think we should take this opportunity as a challenge. Yes, Eric.
Your dissertation work involved a lot of source coding, and your later work is described as comment on why you never should say never, but like behind.
Yeah, I think it's just random. There's no specific reason. In fact, my PhD work started with source coding, but then it became more of a networking problem. So the source coding was not a central part of that work. And besides, there are other people like you who are doing source coding, so let's not go there.
Okay, maybe Li Zhong, last question.
So I appreciate very much what you said about we should reach out to data science. And you quoted Shannon said in his original paper that his work was based on the assumption that semantics are irrelevant. That's where we accepted his definition of entropy. If we're going forward, we want to characterize the meaning of computation. Chances are we're going to abandon those fundamental metrics, entropy, usually mentioned in bits. Are you telling this community that you're willing to do that, or how much we are, have a religion?
I don't know. I mean, I'm not completely sure because I think one interpretation of what Shannon said about meaning is that semantics and so forth is not mathematicalizable. But what I'm saying here is that I don't believe that statement because I believe there's many steps of processing from the message, from the output of the plumbing, to meaning. And certainly some steps may require domain knowledge, human understanding. But there are some parts which are definitely computable, processable, mathematicalizable. And approaches like maximum entropy is useful for those problems. So I'm saying we have the tool, but we apply it in the different ways and solve broader range of problems.
Okay, let's join to thank David again.